All right, good afternoon, everyone. Today will be our last 118B workshop. There will be office hours next week. Those are posted on Canvas, and I made an announcement a little bit earlier about those office hours. If you have any questions, please email me, and we can figure out any additional times if those times don't work for you. I have a little bit of flexibility in my schedule, so we can look at any additional times where we'll be able to meet one-on-one. So today, we'll begin by looking at reactions, or finalizing, I guess, our time looking at reactions of aldehydes and ketones, looking at a few mechanisms, and then we'll try to predict some products. So we're going to start off with looking and proposing a mechanism. We're looking at workshop 18, and we're looking at example 2 and then example 3. So in example 2, we have a species where we have basically two ketones in our molecule. If we were to number our carbons, we can consider this to be carbon 1, 2, 3, 4, 5, and 6. And you can see that adjacent to carbon 5, right, we have carbon 6, which has alpha hydrogens available. So in the presence of base with water and heat, right, we can get our annulation, Robinson annulation, to occur. And for this reaction, our final product is seen on the right. If we were to number the carbons here, this would be carbon 1, 2, 3, 4, 5, and 6. So you'll see that we formed a new bond between carbon 1 and carbon 6, right? So we formed a new bond between carbon 1 and carbon 6, if we were to indicate those on our molecule. Carbon 6 is where the alpha hydrogen is removed, and that gives us an electrophile that can now attack the carbonyl at carbon 1. So if we were to think about the mechanism here, we'll start off with our molecule. And in our molecule, I'll actually draw in the hydrogens now. We'll draw in our 3 alpha hydrogens that are present on that methyl group. And in the presence of base, OH-, we can deprotonate our alpha hydrogen and push electrons to our carbon. This generates a carbanion, a carbanionic species. So we still have our bicyclic ring that contains a carbonyl. And now we have a negative charge on our terminal methyl group. And you can imagine that as we push electrons to if we use our molecule, we can push electrons and we get a new bond forming, right? So we can think of our new bond as forming between our negatively charged carbon, so between carbon 6 and carbon 1, right? And from this reaction, then we'll get, so technically we can think of that as, or actually, when we remove our hydrogen, let's do it a little bit, we skipped a step, right? So when we remove the hydrogen, we'll push electron density here, and then to our oxygen. And this actually gives us a species where we have our vinylic carbon. So now we have O. We want our oxygen here to have a negative formal charge, and now we have a double bond there. And this would be kind of another way that we can show our electron density present as a double bond, right? This would be the more stable form. And then from this, we can have an attack to our carbonyl. And when our carbonyl gets attacked, right, we'll get a molecule now. So now we have our ringed species. So now we have 2 rings. And then on one of our rings, there should be an oxygen, and then we formed another 6-membered ring. From that, if we were to number our carbons, this would be carbon 1, 2, 3, 4, 5, and 6. And then our oxygen should get a negative formal charge. In the presence of water, we can protonate our species, right? In the presence of water, HOOH. We can protonate our oxygen, generating a base. When we protonate our oxygen, now we've generated, I've lost my double bonds, they should be right there, or my aromatic ring. So now we have our 2 rings. This will now be an OH. Now we have another ring here, a methyl, methyl. We have an OH present here. And then in the presence of a base, OH minus, the base that we generated from our water, we can deprotonate an adjacent hydrogen, generating our double bond and having OH as our leaving group. So this gets us to our final product where we now have a double bond that was generated, and we also have ring closing that occurs, right? So for dehydrate, yeah.
Can you please go over that step again, where the bond is formed?
Yeah, so in this step, in the final step, what we're saying is after we've used water to protonate our negatively charged oxygen, so we've used water to protonate our negatively charged oxygen, this generates a hydroxide, right? And we've also generated hydroxide from deprotonating our water. So with this hydroxide, we'll deprotonate an alpha hydrogen to our alcohol, our OH, and then this allows us to generate a double bond. So as we form a new bond between these two carbons here, carbon 6 and carbon 1, we form a new double bond there. We also have the subsequent loss of this hydroxy group OH as OH minus. And you can always, or a good gauge of whether your reactivity you're going in the right direction for your reactivity is if you can regenerate your starting material, which we used OH minus, right? If we can regenerate that OH minus that we had initially, then we know that, which would be regenerated right here from this OH here, then we know that we're kind of going in the right direction. Any questions about that?
Could you, so I was just wondering how in the second step, the double bond kind of like attacked the positive like carbonyl carbon, and then I was just trying to like visualize how the sides fell into place better, because I was having trouble seeing that.
Yeah, so I guess technically an arrow, electron pushing arrow is missing. We'd want to push electrons, so the reaction between the carbonyl carbon here and our double bond is promoted through the regeneration of our carbonyl there, right? To regenerate our ketone there, which is the ketone that we see here. Let's put it in red. The ketone that we see there, that's how we will promote the reactivity between our carbon-carbon double bond and the partially positive carbon in that carbonyl.
Okay, I see.
Yeah, awesome. Okay, cool. So now let's move on to the mechanism for example 3. And in the mechanism for example 3, now we want to look at a reaction where we want to propose a mechanism where we want to look at our molecules. We want to look at our molecules and think about the reactivity with strong base, KOH, with ETOH, ether, in the presence of heat. And we're going to generate a final product here, right? So in this reaction, we want to make sure that our base is deprotonating the most acidic hydrogen. And we have two options for our alpha hydrogens now. So we have an alpha hydrogen present here, and then we have two more available here. If we're thinking about our most acidic alpha hydrogen, it's going to be the alpha hydrogen that's in between two carbonyl groups. So that's the alpha hydrogen that will deprotonate. And we can just use our base, OH minus, to deprotonate that most acidic alpha hydrogen. And when we deprotonate that most acidic alpha hydrogen, we'll form a double bond between our molecule and then push electrons to oxygen. This allows us to generate a new species where we still have our 5-membered ring that now contains a double bond. Our oxygen should have a negative formal charge. And then the rest of our ketone, the other side of our ketone remains the same. And now this can react with our conjugated system, right? The conjugated pi system that we have here. So we can push electrons there, form a double bond here, and then have oxygen get electrons there. And then this allows us to generate a new carbon-carbon bond. So we have our 5-membered ring now, our new carbon-carbon bond, and then this should still be a carbonyl, our ketone, with an isopropyl group, or sorry, with a torpedo group. And then we have a double bond present here. We should have an oxygen with a negative formal charge. And then in the presence of water, we can protonate our molecule. So we can protonate and regenerate our base. And then this allows us to get, we still have our 5-membered ring. We still have our attached carbonyl with our butyl group. Now we have on the same carbon, CH2 CH, 2, CO double bond, right? When we push electrons back to our oxygen, to regenerate our carbonyl, and then protonate our species here, right? Now we have a hydrogen that's present here. So we're just going to draw on that implicit hydrogen. And then the presence of another equivalent of OH, our base, we can deprotonate, push electrons to generate a double bond, and then to oxygen. And this allows us to get our structure where we have our 5-membered ring. Let's make our ring a little bit prettier. So now we have a 5-membered ring, and we have on one side a carbonyl with a tert-butyl group. We should still we should still have a carbonyl present here. And then on the other side, now we have CH2. CH2, there should be a double bond here. Our oxygen now has a single bond with a negative formal charge. And now we can use this double bond to attack our carbonyl here, right? And pushing electrons to our oxygen. Now we have a bicyclic species. Excuse me. So we have a 5-membered ring that's adjacent to now a 6-membered ring. Right, so we have a 5 and 6-membered ring adjacent to one another. We should get a carbonyl present there when we push electrons back to our molecule there. And then this should also have a methyl adjacent to it. And then at our site here, we should have a double bond with our tert-butyl group, right? And you can imagine that we still have, now in this carbonyl, this oxygen has a negative formal charge. We can use water, once again, to protonate it. And then this allows us to generate our alcohol. So now we have an alcohol present on our 5-membered ring, at the bottom of our 5-membered ring, attached to our 6-membered ring. Oh, that's not a 6-membered ring. Let's make it a little bit prettier. So we have 1, 2, 3, 4, 5, 6. So our 6-membered ring, which now has a carbonyl and a methyl. And then this carbonyl remains the same with our isopropyl species. And then in the presence of base that we've just generated, OH minus, we can deprotonate an alpha hydrogen. And always remember that we want to deprotonate our most acidic alpha hydrogen. This generates a double bond and allows our OH to be a good leaving group. And then we can get to our final product where we have our final product that gives us our 5-membered ring. Right, now we should have a double bond present on our molecule, a 5-membered ring adjacent to a 6-membered ring. Right, we should have a carbonyl present there, a methyl there, another carbonyl with a tert-butyl group. And now we've generated a double bond right here with the loss of OH. So this would be our final product.